I welcome everyone once again. Today we'll be discussing correlation. It's a word that we are familiar with, many people, but misconception about the meaning of correlation. And what correlation means to a non-researcher is different from what it means to a researcher. So in statistics, correlation, the meaning of correlation differs from what it means in everyday English usage. So we want to quickly look at some points about correlation. I believe that at the end of the lecture, our understanding of correlation will have improved drastically. In everyday life, to denote some form of association. So correlation in everyday life is a form of association. We correlate them together. It doesn't really matter even if you are dealing with category. The word correlation is used in a loose manner. Then in statistical terms, we use correlation to denote association between two quantitative variables. See, one thing that is very important there, the variable must be quantitative. That is, they must have number as their value. You're going to see that it doesn't have to be continuous. You can have ordinal variable. So far, you have already given number, like when you like SK, you do pain scoring and some other thing, opinion. Once you allocate number, so you can actually use it because it's about quantitative variable, that is variable that have number as the value. So the correlation, if it doesn't have number, you're going to see that in a situation where you just have ordinal variable, there's no way you can rank it. Once you cannot rank it, you cannot talk about correlation because you cannot accrue numerical value to it. So in statistical terms, correlation denotes association between two quantitative variables. We also assume that the association is linear. That is, that one variable increases or decreases the fixed amount for a unit increase or decrease in the other. That is, if this one increased by 2 and the other one increased by 3, if one is another 2, it will increase by another 3. So in a fixed manner. So that is why it is described as linear association. Linear association means that as the value of one increases, the other value either increase or decrease, whichever way. It may increase, it may move in the same direction, it may move in the opposite direction. Those are the two possible ways. But the issue there is that both of them have number. As the number changes, of one changes, the other one changes also. The number changes. It may be that as the number of one increases in value, the other one decreases the value or increases the value. It depends on which direction we are going to talk about later. So regression involves estimating the best straight line to summarize as zero. Why that's how it's different from correlation, but the next slide will show more light to differentiate between the two or so. Now, correlation describes the strength of an association between two variables. The strength, the association, how big it is, what is the strength? So two things, you can have association between height and weight, and it may increase as the height increases, weight may increase. You may have association between blood pressure and age. The blood pressure increases, the age increases rather, the blood pressure may increase. But the strength of the association between the two may not be the same. So what correlation do you to measure, quantify the strength of association between two variables? Correlation is completely symmetrical. That is, if you say correlation between A and B, it's the same thing as correlation between B and A. It doesn't really matter which one you say first. Even when we want to plot them, put them plot them, it doesn't really matter which one is along the vertical axis or which one is along the horizontal axis. The issue there is that it just is symmetrical in the sense that the correlation between A and B is the same thing as correlation between B and A. Now, if you are talking if two variables are related, because what we are looking at, we are trying to differentiate association and relationship. Correlation look at the strength of association. But if two variables are related, that is, there's a relationship, it means that when one changes by a certain amount, the other changes on an average by a certain amount. And in this case, whenever there's a relationship, sometimes you see, when you say there's a relationship, there's defined each party has a role. In a relationship now, when we are talking of regression, we're going to realize that one depends on the other. You can predict the value of one from the other. For instance, in the children described earlier, greater, okay, I think I give an example later. I will come back to it. If y represents the dependent variable and x the independent variable, this relationship is described as regression of y on x. So now, if we are talking of regression now, in relationship, there is one that is dependent variable, there is one that is independent variable. But in a correlation, it's not like just a strength of association. It's not actually looking at relationship. You are not predicting one from the other. Because if you cannot say, because we have already said that B, association of B and A and A and B is the same. So you cannot say that you derive A from B or derive B from A. It's just that they are associated. That is correlation. But in relationship regression, you derive value. Like for example, when we are talking of age and blood pressure now, you cannot say the blood pressure determines somebody's age. Rather, the age will determine the blood pressure. In that case, the age is the independent variable, the blood pressure is the dependent variable. A measure of how much two random variables vary together. So we want to quickly look at understanding the concept of covariance, because you're going to see that the origin of correlation is actually from covariance. So for you to know how people invented correlation, be able to understand, it's good to understand the concept of covariance, because it was actually invented from covariance. So a covariance is a measure of how much two random variables vary together. That is, you have, let's say, age, or let's say height and weight for children now. As the height changes, the weight changes, what of the height? They vary together, they increase together or decrease together. So the measure of how much these two variables vary together in the same group of people or the same person is covariance. It's similar to variance, but variance, because variance also talk about variability. But variance tells how a single variable varies. That is, it's like a height now. How height varies among people, among children. How weight varies among people or among children. That is variance. But covariance is talking about two variables, maybe height and weight. How do they vary among the children? And so now, variance talk about variability of a single variable, while covariance tells about how two variables vary together. So if you plot in covariance now, since you are talking of two variables, you can have a plane figure like something that vertical and horizontal. If you plot, if they vary very well and they move in the same direction, they give if they very perfectly vary together, to be on a straight line, the slope will be going up to move to the right. But if it is in the as one increases, the other one decreases, it will be on straight line also, but to slope down. If there's no covariance, there are no covariance, they don't covary, the plot will be scattered. One increases doesn't mean the other one will increase or decrease. So you see the one in the middle. You will see that when you get to correlation, it looks like the same thing, but you're going to see the difference between correlation and the covariance. Now, let's quickly illustrate covariance and covariance. Since we say there are different, there are things that are similar there, both of them their measure of variability. The variance is about variability of one variable, variability of two variables together. Let's, for example, let's look at maybe a product was being advertised, and you look at the number of advert watched by individual. So we have 5 people now, just for simple illustration. 5 subjects, 1, 2, number 1, 2, 3, 4, 5. So you start to see the number of advert of that product each of them watched, and eventually the number of product packet of the product each of them bought. You want to see the number of adverts watched is a variable. So the number of packets of the product bought is a variable. These two variables, they co-vary, they vary together. You can see it in the graph like this. You can see for the first person watched 5 and bought 8. The second person watched 4 and bought 9. The third person watched 4 and bought 10. The fourth person watched 6 and bought 13. And the last person watched 8 and bought 15 pack. If you try to plot this number of advert watch and number of product bought, packet of the product bought, on the look at it. You know, the mean is usually the same across. You see that the mean for this blue plot, talking of the advert watch, you remember the mean is 5.4. Look at, if you look at the scale, the mean is between 4 and 6, 5.4. Can you see? It's around that 5.4. If you look at the number of advert packet bought, which is this green plot, you see the mean is 11. Can you see the position at 11? But you see the position of each, the value of each person subject. Like for this one now, when I watch 5, can you see the value is a little bit less than the mean by 0.4, but the mean is 5.4. The person that watch 4, look at it also, it's below the mean by 1.4. That's why it has negative mark below the mean. The person that, okay, 2 of them watch 4. The person that watch 6, can you see? Because it's above the mean by 0.6, can you see? And the person that watch 8 is above the mean by 2.6. Can you see the direction? But if you now consider the packet bought also, the person that bought 8, and you see it's below the mean because the mean is 11 by 3. That's why it's minus 3 there. And the person that bought 9, below the mean by 2. Then the person that bought 10, below the mean by 1. The person that bought 13 is above the mean by 2. So the mean is 11. And the person that bought 15 is above the mean by 2. You will see the direction of where initial set. Can you see in the initial set of the first 3 people, the number of advert was below the mean, and the last 2 people is above the mean. Whereas for the packet bought, it's the same thing. The first 3 people below the mean, and the next person above the mean. You can see the way the flip is in the same direction. You can see even from the picture, you can actually see that, oh, this thing could vary. You can see that number of advert watch and the number of packets of the product bought could vary. And you now begin to think about direction. So as one increases, the other one increases. If let's say it's in the opposite direction, what will happen is that for this number of advert watch, the first 3 that are below the mean, if they are in opposite direction, the number of packet bought is opposite direction. This one, the first 3 of the product bought will be above the mean, and the last 2 people that the number of advert was above the mean, then their product bought will be below the mean, to be facing. What this one will be in opposite direction. You can now say, oh, they covary, but it's negative covariance. But here now, what we are seeing, there's the covary, but it's a positive covariance. If it's going to be 0 covariance, if they don't covary, you will just see a haphazard pattern. You're going to see this one can be down, this one is following it, this one is down, this one is opposite. just scatter. You cannot see a pattern. That shows that there's no covariance. That's just a pictorial illustration. But how do you compute it? This example now, I put it there. Look at it. These are the X, the number of Albert was. When you want to variance, you remember the formula for variance is, how do you say X minus X bar, that is the mean. You remove mean, you look at deviation from the mean. The mean is the expected value. When value is no hypothesis is true, the mean is the expected value. So you remove the mean by X from X and square it. When you square it, you sum it together and divide by the degree of freedom, which is n minus 1. So we are not going to be talking, because the last lecture was extensively on the degree of freedom. I'm trying to correct something. On the degree of freedom. So I will not talk about much about the degree of freedom. That is n minus 1. The degree of freedom here is n minus 1. Now, you will see that when you now talk about the covariance, that's the formula for if you talk about covariance, this first formula you're talking of how one variable, it can be X, you can denote it by X or Y, but this one we denote it by X. How you calculate it here. From the same, instead, if you look at it, you X minus S bar square. But in covariance, we are looking at variance with how two variables vary together. So you split one part. You know, X minus S bar square just means X minus X times X minus X. That's what it means. You multiply you square the deviation. So covariance will now be X minus S bar multiplied by Y minus Y bar. Now, if it is variance for X now, it will be X minus S bar square. That is X minus S bar times X minus S bar all over the degree of freedom. If it is for Y, it will be Y minus Y bar times Y minus Y bar over the degree of freedom. But since it's covariance now, it's X minus S bar multiplied by Y minus Y bar over the degree of freedom. So if you compute it from what we are doing, it gives you 4.25 for the covariance. So since it's a positive thing, so we can say that both of them increases together or decreases together. If it has given us a negative value, it shows that both of them, if one moves in one direction, the other one moves in opposite direction. But we have problem interpreting covariance, and that is why it's not popular. We want to see the reason how people now jettison and now move to correlation, derive correlation of covariance. The problem in interpreting covariance, lack covariance can mean a strong relationship between a variable. Yes. However, you can compare variances over data set with different scale, like weight and height. We cannot, like, if you want to talk about, you say weight and height. You cannot even compare their variances. Not to now talking about, because weight in kilogram, you'll be having value like 70, 80, 60. Height in meter, you'll be having value at 1 point something. If it is height in centimeter, you'll be having value of 170. So they are not in the same scale. So if you are looking at distance now and time, you will see we are talking about 1,500 kilometers, and maybe you are talking of 8 hours, 20 hours. So you will discover that the covariance the value depends on two things. It depends on how big the value of X and Y. It also depends on the unit of measurement. If naturally the unit is big, it just gives a value. So it's difficult it's not standardized. So a weak covariance in one data set may be strong in another. The main problem with interpretation is that the wide range of results that it takes to make a hard is very interpreted, because the value depends on the unit of different things you are measuring. So because of that, it's not universal. So the larger the X and value and Y value, the larger the covariance. The same thing, the unit of measurement, the higher, the larger the unit of measurement of X and Y, the larger the covariance. So how do we fix the problem of interpreting covariance? How do we fix that problem? So intelligent people came. Okay, that's okay. Since problem, the best way to do is to standardize. If you remember, when we talk about normal distribution, when you want to, instead of you talk about maybe many things follow normal distribution: weight, height, IQ, distance travel, blood sugar. Think of many things that follow. Most biological phenomena and social science phenomena, they follow normal distribution. But even though they follow, if you are to plot the normal distribution, it give you different value because each of them have different value. So the solution was similar to what happened here. So instead of now quoting somebody's value, a particular value like for weight now, instead of saying that this person weight 8 kilograms, you don't look at what is the difference between this person's weight and the mean weight of the population. Once you know the difference, then divide by the standard deviation of the population. So it gives you a number of how many standard deviation away from the mean. It's standard. That's what they call z-score. So when you do that for all variables, they follow that standard normal distribution. So how do you standardize those variables? By dividing the difference between the value and the mean, you divide it by the standard deviation to get the set. It's the same thing. Here, if you want to standardize covariance, since the problem is the unit, the problem is the unit, different variable have different unit. You divide that covariance by the standard deviation of the x and y also. Since you are looking at the covariance of x and y, you divide by the standard deviation of x and y. If you do that, it gives you correlation. That is the origin of correlation. Look at the formula for covariance we use here. You divide by the standard deviation of x and y. When you arrange it, gives you this, which is the correlation. So this is correlation. The issue about it is that it has cancelled out the unit. You know, if you you can see the numerator is the x and y there. Denominator x and y there. So if you are talking of weight and height, so kg and meter form part of the numerator. Kg and meter form part of the denominator, so it cancels out. It gives you a ratio. Look at this, just like this curve. It gives you a dimensionless. That's no unit. So correlation does not have unit, and it's not affected by changes in the center. It's not affected by changes in maybe the mean, especially if something is skewed or scale of the variable. So now that is, you can see that correlation is standardized covariance. You standardize it by dividing by their standard deviation. If you have questions, you can be writing it. So I will stop, entertain the question. Now, what does that correlation mean? The degree of linear association between two variables, as I've said, the strength of the association is summarized by the correlation coefficient. The correlation coefficient is a dimension. That is, it has no unit. It ranges from -1 to +1. So the issue, the logic there, the numerator can never be bigger than the denominator. The denominator can be bigger, but the numerator can. So if the numerator cannot be bigger, because it is when the numerator is bigger than that you now have value greater than 1. Cannot be greater, so it's from 0 to 1. From the value, the quantity value. So, but if it is opposite direction, it will be minus. If it is negative direction, it's plus. I think if it is positive direction, those are both of them increases together or decreases together. Both of them increase together. But if it is negative, that shows that they are in opposite direction. The best way to explain it is inverse proportion and direct proportion. You know, you remember your secondary school when in mathematics you talk about inverse proportion and direct proportion. In direct proportion, two variables vary together. One increases, the other one increases. That's direct proportion. In inverse proportion, two variables vary in opposite direction. As one increases, the other one decreases. or the other one decreases, this one increases. So they always move in opposite. That is inverse proportion. So positive correlation is the direct proportion. That's why the negative correlation is inverse proportion. So if you remember your physics and chemistry, the Charles law and Boss law. The Boss law, Charles law is like direct proportion. We talk about the pressure and the temperature. The temperature increases, pressure of gas increases. So both of them increase together. So if the temperature decrease, the pressure will decrease also. So they move in the same direction. That is direct proportion. That is positive correlation. The Boss law talk about the volume and pressure. As the volume increases, the pressure decreases. As the volume decreases, the pressure increases. So volume and pressure, Charles Boss law, move in opposite direction. So that is inverse proportion. Example of negative correlation. Many people, you see many books, say that the value, like the way I put it, the value ranges from -1 to +1. But to me, in calculating it, I don't think the value ranges from, because if a particular correlation is going to be negative, it's going to be inverse, it will not have possible value on the positive side. It will not have possible value on the positive side. If a relationship, maybe a correlation is going to be direct proportion, direct, that is positive correlation, it will not have possible value below 0. It's going to be 0 to 1. If it is inverse, it's going to be between 0 and -1. So the value is actually between 0 and 1, but it can be positive or negative. So the men will just, okay, the value ranges from positive value from -1, whichever way, just for you to have the understanding. A positive correlation is one in which both variables increase and decrease together. I think I said it. A negative correlation is one in which one variable increases and the other decreases. Now, when variables are exactly linearly related, correlation coefficient equal that +1 or -1. What do you mean? Perfectly related means that always, as this one must increase by certain all the time, always. That is perfect. But if it is as this one increase, the other one must increase by certain and decrease by certain amount, that is in opposite direction, always that will be negative, perfectly -1. But it's not always all like that. Know that the correlation coefficient is unaffected by the unit of measure. I have said that one. It has something, so it is universal. It's used in engineering, in medicine, in agri, in social science, in different fields. Just like the Z-score is universal when you talk about odds ratio, relative risk. Because they are all ratio. All those things that are ratio, they are universal. So the square of the correlation coefficient gives the proportion of variation of one. Yeah, okay. This one, you know, but I said this is what we call coefficient of determination. It will be explained better when we get to regression. When we get to regression, the square of correlation is coefficient of determination. It's just one way of, that is just one way of calculating it. And what it gives is a variation in one variable that is accounted or explained by the variation in another. So look at scatter plot. I try to show if you plot the value pictorially in the graph. If it's going to be positively correlated and perfect, all of them will just slope up on the line. If it's going to be negative, it will be on line, slow down like this. But look at this one, 0. You cannot see a pattern. And when you cannot see a pattern either up or down, it's 0. But look at this one. You can still see a pattern down, but they are not on a straight line. It's negative correlation. It's minus 0.8. Can you see? Look at this one. It's scattered somehow, but you can still see that it's going up. This plus 0.3. But if it's online, that would be 1. Either positive or negative. Okay, online. Now, the same thing. Look at example, positive, negative. Then sometimes it can be curved line. Sometimes. Then let's quickly look at correlation coefficient. Note say the strength correlation is measured by the coefficient. That particular thing that measures the strength, that strength of association is the coefficient. And the first person to describe this correlation is Pearson. I know when we talk about, I think we first published this in 1920, something like that. Then I talk about, is it 19 or 1820s? But we talk about it be the origin of chi-square. Yes, Pearson, Carl Pearson. So that's why the mention of Pearson chi-square, Pearson Proudhon moment coefficient, correlation coefficient was the first to describe it. And so the first one that is applicable to quantitative variable was first described by him. And the another type, I will explain them later because this just table just to show it, because into detail you see the logic. But that I think was the first to explain how you get correlation covariance, because that formula we derive is the Pearson, which is represented as R, Pearson correlation coefficient. That particular formula where we derive correlation from covariance is actually, that correlation is Pearson product moment correlation. If you look at product here, you're just multiplying, you are multiplying the two deviation. Yeah. Spearman, in a situation where the data does not follow normal distribution, we will be talking of, rather than talking of Pearson, other people came with solutions like Spearman and Kendall. Where Spearman is more applicable whenever, okay, discrete variable like number of children, because it's not continuous. You can use it, but when we are talking of rank data, we use Spearman also, but whenever a lot of tyrant in the right one rank data, and the sample size is very small, Kendall will be better. Then we have something very interesting. The last two on this, very, very interesting. Point biserial correlation coefficient and biserial correlation. When we talk about point biserial, it's talking about correlation between one quantitative variable and another categorical dichotomous variable. Point biserial, discrete dichotomous variable. So when they say discrete dichotomous variable, something like sex now is dichotomous variable, is discrete in the sense that there's no underlying continuum. There's nothing. It's not as if maybe they did something, there was a number, they divide, they have a cutoff to get male and female. Male and female just two categories of sex. So if you sometimes you want to correlate blood sugar and sex, yes, you can do that. But that is a form of point biserial correlation. So all you need to do, one of the sex, you code it 1, the other one 0. In doing it, you can do that. But of course, you have to know the one you code 1 or 0. Because it will give you the same answer, but the interpretation. If you code it male 1 and female 0, the way you interpret it will be different from you code 1 and female 0. Then, biserial correlation coefficient. This one is quite interesting also. This one is an association between quantitative variable and a continuous dichotomous variable. There's a dichotomous, when you say dichotomous, there are two possible values. Just like the sex also, that anything that have yes or no, dead or alive or whatever. Think of any two possible values. The first one, point biserial, those categories, two categories, they are just there. There's no underlying quantitative value. But this second one, biserial correlation coefficient, where there is a continuous variable and a continuous dichotomous variable. The meaning of continuous dichotomous variable is that there is a continuum underlying the two categories. For example, you say diabetic, non-diabetic. But the people you divide into two, diabetic, non-diabetic, what you mentioned before was blood sugar. When you not see anybody that have blood sugar 126 and above, diabetic. Anything below 126, non-diabetic. So there is a continuous value underlying the decision. And that is, we call that type of variable a continuous dichotomous variable. So like blood sugar is a continuous dichotomous variable. The same thing with BMI. You do BMI, you just have a cut to say obese, not obese. The same thing with hypertension. Though the hypertension is dicey, okay, let's say systolic hypertension or diastolic hypertension. But the issue is, see the same principle, because you measure blood pressure. Any blood pressure above certain value has the attribute. Below, don't have the attribute. The same thing with anemia. So you are studying the rate of anemia. You with hemoglobin concentration below certain value or PCV below certain value, you say they are anemic. While people with value above that value, non-anemic. So all those anemic, non-anemic, hypertensive, non-hypertensive, diabetic, non-diabetic, they are a sample of continuous dichotomous variable. And when you do the correlation between like that and the continuous variable, that is a biserial correlation. And this person, I think I will stop here, because maybe by Tuesday we talk further on maybe how to compute, then talk about some other things about correlation. So we still look at the difference between the Spearman, Pearson, Spearman, and even Kendall. Look at different ways of computing them. But this weekend also we are going to have, starting from tomorrow, is a workshop on correlation and linear regression. We'll be able to run the analysis, have a scenario, and you see the way you compute it with the value, and at the same time you run with SPSS. So you see how to work it, basically how to run it. So it makes it stick, and that's what we do. That's why we call it workshop. So, and that's very exciting. And we have this weekend, first batch, second batch next week. Okay, before that, because we are still recording, let's entertain question before I talk about general things. So I see somebody chatted. Good evening. Okay. Any question? No question? Any question?
Good evening, sir. Thank you very much, sir, for this session.
Okay, good evening.
Sorry, sir, I know that I came in late, but I just want to confirm. Okay, thank you very much, sir. So for the correlation, I'm just trying to remember. I know you said it is to test a linear association. So would that then be that it's a test for between two continuous variables? Is that what it means?
Because
is that what it is for?
It has to be two quantitative. It doesn't have to be continuous. It must be quantitative. The value must have number.
Okay, quantitative, sorry.
Yeah, it doesn't have to be continuous. When you are dealing with continuous, I will now talk about Pearson. But when you cannot see one is, see, I've already given an example of biserial different way. It doesn't have, all of them it don't have to be continuous. But if it's continuous and continuous, that's Pearson. But in the situation where we have some district or category which ordinal, like when you have your Likert scale, already 1, 2, 2, 5. It's number also. It's number. So you can do Spearman or Kendall's correlation. So far, those variables, they are number. So any variable that you don't give number, you cannot do correlation. You don't have to do with number. Even if you look at the point biserial and biserial, one is continuous, the other one is dichotomous. The dichotomous, the way we do is 1 and 0. Yes, and if you want to do correlation between sex and blood sugar now, blood sugar will be the continuous variable. The sex, we can now say female sex coded as 1. So in that case, I want to see correlation between female sex and blood sugar. I will now code the female sex as 1, the male 0, right? So it's a form of point biserial. Yeah,
it has to be 1 and 0 because.
No, that's in a situation where you are using one of them is dichotomous. That is when we are talking of binary variable. Binary, only two possible values, like male and female, diabetic, non-diabetic, dead or alive, obese.
And it has to be 1 and 0.
Yeah, if you want to do, one has to be 1 and one you have to be 0. Yes, I mean, because correlation
Okay,
is about
it
number.
it cannot be one or two. Oh,
No, it's
hello.
not, it cannot be one or two. In fact, it will destroy it because it will be, if you put 1 and 2, it will look as if you are looking at a sperma
Yes.
correlation where there's a rank, that 1 and 2 is rank, but they are limited option. But actually, when you even have, you don't have, you cannot say something is ordinal unless you have 3 categories, at least 3. Yes, and if you put 1 and 2, it's not ordinal.
Yes.
Yes, I'm now. So that one does not make meaning. But for you to even say ordinal, you must have at least 3 points. 1, 2, 3. Can be 1, 2, 3, 4. Well, you know, when you are ranking, you start from 1. You are ranking, you start from 1. 1, 2,
Yes.
3. So if there are 10 categories, you can say 1 to 10. So yes, since correlation is not influential, does it? Yes, Dr. Prof said yes. And we'll talk about that on Tuesday. Yes, we need, when after you are done correlation, you have to test. UT test to test. It's part of what we'll be discussing. UT test to test will be significant. But you're going to see that one has to be careful about correlation p-value. The p-value of correlation is dicey. And that is why most literature, you don't use the p-value. You rather, intelligent people now try to grade the correlation. Anything less than, from 0 to 0. Less than 0.2 is eligible. 0.2 to 0. Maybe 5 now. Say mine, 0.5 to 0.8, moderate, 0.8 to 0.99, strong, 1, perfect. So the grade like that. Because the reason means that if the value of the p-value depends on the sample size in correlation. If the sample size is very large, a small correlation will be significant. Even though you say the correlation is 0.01, very small, it will say it's significant because the sample size is large. If the sample size is very small, even big correlation at 0.8, it may not be significant because the sample size is very small. Can you see? So somehow. So interpreting correlation, even using the p-value is useless. So people don't use it, even though you use test to do it, but people don't base decision on that because it's misleading. So whether it's going to be significant or not depends on the sample size. Okay. Any other one?
Yes.
Okay, go on.
Can you hear me?
Yes, sir.
If I know that we are going to do it the weekend, but I just want to ask if correlation is positive, is it mandatory for you to do something else, maybe regression, or you can leave it like that at times?
Okay, that's a very good one. You know, a lot of things, that's why statistics actually is an instrument. Yes, I mean. So that's why they say statistical significance is different from clinical significance. That is why, if you remember when we talk extensively about sample size determination, there are places where clinical judgment comes in. Like now, if you are looking at 2 variables now, it's not the statistic that will tell you which one is exposure, which is the one outcome. It's from sense, and that sense computer, the statistic does. Statistics is an anime, just subject that people. So even the computer, the program, they are not intelligent like people to decide. So like for whatever program they put there is human being that put it. Like now, I made mention of blood pressure and age. Which one is dependent? Which one is dependent? Of course, age cannot depend on blood pressure. Is it age that determine? Is it blood pressure that determine how old you are? No, but how old you are may determine your blood pressure. So in that, when you look at the association between the two now, you now know that okay, age will determine blood pressure. So when you see association like that, it's you that will think very well, literature, many things, to really know these 2 variables, are they related? Because they may be related or they may be association. They may not be related, but they are association. It's just like the way we are in this lecture now. You have a lot of people you have never met. On this Zoom now, you are meeting people that every week You come together, you see the person, before you know it, you begin to get familiar with the person. You know, you just know that, well, yeah, there's this Dr. Oluwaseun. Yes, we used to attend lecture together. That's an association. It doesn't mean that you are related or anything. It's an association. So there must be, if there must be a factor. Why is it that wherever you are, Dr. Oluwaseun will be there? There must be another factor. And that factor is this lecture. Yes, is the confounder, showing as if there's a relationship between you. So that is why sometimes when you do association, you can even have strength of association is very light. The correlation is very strong. They may not even be related. In fact, it does not mean causation. You have to do extensive literature review and look at, bring other factors in to find out. So for the fact that something is significant doesn't mean it makes sense. That's what we call biological plausibility. Something that doesn't make sense. Well, there's something that may not make sense, but it may not be that, it may be that you don't know. That one, we know that. But in most cases, you cannot categorically put your hand down and say this unless you're able to relate it with results, because you can easily tell lie with statistics. That's why Disraeli said that there are three kinds of lie: lie, damn lies, and statistics. You can easily tell lies if you don't understand what we are doing. So whether you're going to do regression is another thing. So it depends on your extensive literature review. You know, you place this variable, you know the relationship, there's something that are very simple. Like you cannot say that socioeconomic status, you say your sex, socioeconomic status determine your sex. How can it? If somebody is born male or female from conception and delivery. So, but that sex may not determine somebody's socioeconomic status. But socioeconomic status cannot determine the person's sex. So if there's a association between them, there are something that you cannot even tally. It doesn't even tally. That shows that it's just like they say that people say that when there's a correlation, strong correlation between drowning, the number of people that drown, and the number of sale of ice cream. So how is it something? So the issue is that maybe season may be a confounder. The season. So the time people drown, maybe there's a particular season, and there's a particular season also people tend to buy ice cream. So if you have a large group of data, just running, just see association. It doesn't mean that they even have anything in common. It's just like that. Are we together? Are we together?
Yes.
Like somebody you are traveling.
Yes.
Play with somebody.
I can answer you. I'm answering you.
Okay. So I think it's clear. Have I answered your question?
It's clear. It's
Okay,
clear. It's clear.
Okay, that's great. Okay, any other one? Any other one? Okay, there's no, that is very straightforward. So if you have question, you can text it. So by yes.
So will you go over this during the workshop? Will you go over this?
You are asking as if you have never attended the workshop. Of course, everything. The workshop we have more time.
The workshop is more extensive.
Exactly, that's what let me tell you how. It's more extensive because we have the time, because we have much time to go into the detail. Even that
workshop
one
is more extensive
because
the hands-on.
Exactly.
With hands-on training, illustration, example.
I know. No. I the reason I ask was I didn't know if it's
you don't have any hands-on training there.
Type. You know,
I can't hear you. What do you say?
Okay. Maybe you didn't understand my question.
What's that?
I said maybe you didn't understand my question. You know that I will say, sometimes you might give a different lecture for the workshop. Maybe there are two lectures. So I was like, is it this one we're taking or the other one?
Which one? Which the other one? Okay, if I want to do workshop on
logic,
on correlation and linear regression, all the things I've said I will still say them. I will explain what correlation means, and that one we even have example. We run, we solve, and run. So there's nothing we are saying here we will not see. You know, I don't know if you understand.
The way I understand is that what she's saying is that might be there will have been a lecture on regression before workshop.
No.
She's asking
Okay,
whether you are going to do this all over.
No. There's no lecture. But we'll explain regression also. There, I will explain the regression. You know, the lecture, Tuesday lecture, is to bring out something that I feel that people will benefit from, right? So, like now, we are talking about degree of freedom. Maybe by Tuesday, we'll still finish on correlation. Maybe the Thursday, I may talk about regression. Yes, and if after that Thursday coming week is the time for the next for the second batch. Yes, and now. So by the time we are moving to the other week now, where we're going to do logistics, I may talk something about logistics, right? Just to give. I may not talk about logistics lecture. I may not talk about logistics. I may talk about something I feel is necessary for people to have understanding. Do you get the picture now? So most of the things I say, the workshop usually tailor everything because the workshop you are practicalizing everything there. Okay, no problem. Any other one?
Thank you.
Welcome. Okay.
Okay, thank you.
Okay, let me just pause it for you.